Welcome back, everyone. In the last lecture, I explained the concept of linear dependence and independence of vectors. So, if you haven't watched that video, then please watch it because in today's video, I am going to solve previous year questions on linear algebra for GATE DA. So, those concepts will be highly useful to solve these questions. Okay, firstly, you all might be thinking that DA is a new paper, so how I am getting PYQs. So let me clear this. Linear algebra is part of many paper codes like computer science, mechanical, electrical, etc., etc. And most of the syllabus is common with the DA linear algebra syllabus. So all these PYQ, which I am going to cover, are actually PYQs for other paper codes. Okay, but they are completely useful for DA as the syllabus is same, and also all these paper codes are set by IIT professors. So you will see similar question across all these paper codes for the same subject. All right. Okay, in today's video, I will be covering four very important PYQs on various topics: linear dependence, independence of vectors, linearity, and linear transformation, and all. So let's start. Okay, so the first question is here on your screen. So it is saying check whether we are given a mapping. Just give me a minute. Yes. So we are given a mapping, and this mapping is from R3 to R2. Okay, this V is vector space. Okay, from R3 to R2. R basically denotes the values are real values, not complex. Okay, so we are given a mapping from R3 to R2. So F is a mapping from R3 to R2. Okay, and the mapping is uh, just give me a minute. The mapping is given as uh, F A comma B comma C is C comma A plus B. And you can also see that how this is from R3 to R2 because in the input vector space we are taking three values, right? A comma B comma C. This is three values. This is coming from R3. The vector length is 3. Whereas in output we have only two values. The first value is C itself and the second value is A plus B. So you can see that input in the input space we have three values A, B, C, whereas in output we have only two values C, comma A plus B. So we need to find whether this particular mapping, this particular function is linear or not. Okay, so this f is nothing but a linear is a transformation, and we need to check whether this transformation is a linear transformation or not. Okay, we have seen a property of linear transformation in previous lectures, right? So the property I will show you. This is a property, right? So if T is a linear transformation, if C times V plus D times W, this is a linear combination, right? V and W are vectors and C and D are scalars. So the linear combination C times V plus D times W is nothing but it can be written as C times the transformation of vector V plus D times the transformation of vector W. Okay, so we will apply the same property here to check whether this is linear or not. Okay, so let us suppose let's take two vectors in the input vector space. One is alpha, which is A1, B1, and C1. Okay, this belongs to the input vector space V3, right? And let's take another vector in the input vector space beta, which is A2, B2, and C2. This also belongs to the input vector space V3, right? And we have to take in the input vector space because the mapping is from V3 to V2, so we have taken a three-dimensional vector, right? Okay. Uh, now we need to check whether this f a times alpha, which is the input vector alpha, plus b times beta, right? we need to check whether this becomes a times f of alpha plus b times f of beta or not. Okay, so we will expand this expression. So this becomes f. Now we will simply write a and then the vector alpha and vector beta, which is a1, b1, and c1, right? Then plus b, the vector beta, a2, b2, and c2, right? We will expand this a1 plus b times a2, right? So we have taken a1 here and plus b times a2, right? Similarly, this become a b1 plus b times b2, comma a c1 plus b times c2, right? Now we will further simplify this. Uh, we will take a times c1 plus b times c2 and then a times a1 plus b times a2 plus a times b1 plus b times b2. Now you may be saying how I got from this step to this, because if you see what is f of abc, f of abc is nothing but c comma a plus b. So what is f of this? Now you can think of this entire thing as a, this entire thing as b. Uh, you can think this entire thing as one entity A, this entire thing as another entity B, and this entire thing as another entity C, right? And we have seen that f of A, B, C is nothing but C comma A plus B. So this entire thing is C. So I have taken this in front, and this entire thing is A, this entire thing is B. Then I simply added them, right? So this is nothing but it is given in the question itself that f of A, B, C is nothing but C comma A plus B, right? So I just use that transformation I mean basically that mapping. Okay, now I will further simplify this a times uh, c1 comma a1 plus a b1. But basically what I basically did is I taken all the terms with a uh, in them and I simply added, and from here onwards it's pure algebra. All right, nothing else. It's just solving algebra. All right. Now I will simply take a outside, and this will become c1 a1 plus b1. I will simply take b outside. This becomes c2 comma a2 plus b2. And now if I see, this can be written, this c comma a plus b can be simply written as f of a1 comma b1 comma c1, right? Why? Because f of abc, what is f of abc? It's nothing but c comma a plus b. So if f of abc is c comma a plus b, then f of a1 b1 c1 will be c1 comma a1 plus b. So I have gone from right to left, right? So c comma a plus b can also be written as f of a comma b comma c. Okay. So similarly, this can be written as b times f of a2 b2 c2, right? And this is nothing but a times, what is a1 b1 c1? A1 b1 c1 is nothing but alpha, the vector alpha. And so this can be written as this, and plus what is a2 b2 c2 it is nothing but the vector beta, right? So this can be written as f of beta. Now you have now you see that we have proved that f of a times alpha plus b times beta, that property which I have just told you, this property t times cv plus dw, this property, right? So this property basically uh, t times uh, a time v uh, plus b time w uh, is this. This is the linearity property. Okay. And we have proved this, right? We have just proved this, that f of uh, I just I will just rewrite this, that this basically we prove that f of a times alpha plus b times beta is nothing but a times f of alpha plus b of f of beta. We just proved this. So then we can simply say that we can say that f is linear. Therefore, f is linear. It's a linear mapping or linear transformation. Mapping are also called transformation. Those are same word, mapping, transformation, and functions. Okay. So I think this question is clear to you. Okay. Now we will go to the our second question. Okay, I will also recommend you for every question, it's better you just pause the video and first try solving by your own, and then resume the video and see whether you are able to solve it correctly or not. Okay. Now, what concept is applied in this question one? It's the linearity property concept. Okay. Now we go to the second question. So it is saying that find matrix representation of linear transformation. We are given a linear transformation T, which is given as T A comma B comma C is 2B plus C, A comma A minus 4B comma 3A. So this is the linear transformation. And first of all, this T is from R3 to R3, right? It is from R3 to R3. Because input we are giving a three-dimensional vector ABC, and in the output we are also getting a three-dimensional vector. Okay, so we need to find the matrix representation of this linear transformation corresponding to this basis, and this basis is standard basis, right? So this is relatively simple question than the previous one. So the transformation T is given as T A comma B comma C, uh, 2b plus c, a minus 4b comma 3a. Okay, so basically for these bases we need to check how these bases are getting transformed. So how T100 is getting transformed. So it is simple. You just apply this formula. You will get 0, then 1, then 3, right? Similarly for T010, you will get T2 minus 4 comma 0. I am just simply applying this formula. Okay, so for example, this 100, B plus C becomes 0, then B is 0, A is 1, so this becomes A, then A is 1, so 3 times A is 3. All right, then T 0 comma 0 comma 1 is 1 0 0. All right. Now, if you have seen my videos, then the matrix, what does the columns of matrix represent? The first column represent where the first basis vector landed. The second column represent where the second basis vector landed, and the third column represent where the third basis vector landed. So where the first basis vector, this is the first basis vector, where it landed. It landed at 0 1 3, right? So basically the first column becomes 0 1 3. That's it. The second basis vector landed at 2 minus 4 0, so the second column become this. That's it. And that similarly the third column become uh, sorry, yeah, the third column will become 1 0 0, right? So this is 0, this is 0, yeah, that this is fine. So this is where the first basis vector, this is second, this is third, and in this case the basis vectors are I hat, J hat, K hat. So I can say where I hat landed, right? Because our basis vector itself are I hat, J hat, where J hat landed, and this column represent where K hat landed, right? That's it. And that's all in this question. See, this type of question, the first question is important. This can come in gate DA very easily. The second type of this question won't be come directly because this is pretty simple. But the way you create these matrices is important because these can become a part of some bigger problems or complex problem. You will see in problems related to change in basis, how you construct these matrices from transformation is important, because these are intermediate step while solving other questions. All right. Also, you can also see this can be written as in terms of basis, as like we have this standard basis, right? So I can simply write this as like this. So this transform vector is nothing but the 0 times the first basis vector plus 1 time the second basis vector, 3 times the third basis vector. If you solve this, you will get this only. Similarly, you can do for the second and third one. All right. So this one is a simple question, but yeah, it is important because they are helpful in solving bigger problems. Now the third question, guys, like this is very important question. Just mark this down. These types of questions are going to come in GATE for sure. The first question is also important. This can also come. But this is very interesting question. Like very interesting question. All right, we will solve this. Okay. So what is given? Also, which concept has been applied in this particular question? Question 2 is simple linear transformation concept, nothing else. The third question, very important. This question is on linear dependence and independence, which I explained you in the last lecture. So let's see if you are able to solve it or not. Pause the video and try to solve. Okay. Okay, the question is if the set we are given this set. So this set is set of matrices. Set could be of anything. It could be of number, it could be of strings, it could be of objects, it could be of matrices. So this is a set of matrices. We are given three matrices, three 2 by 2 matrices. Okay. And it is given that it is linearly dependent. Very important. It is already given that this set is linearly dependent. So if the set is linearly dependent in vector space of all 2 cross 2 matrices, so this is the vector spaces of 2 cross 2 matrices. See, vector space is an abstract concept. Vector space could be of anything. It's just not about vectors. It could be of vector space could be of matrices as well. Vector space could be of functions as well. Vector space could be of any custom object. So you just need to fulfill certain properties. If those properties are fulfilled, then it's a vector space. Okay, so in this case, this is a vector space of 2 cross 2 matrices with real entries. This is also important. It's real entries. So you cannot have complex entries there. Okay. So it is given that this vector this is a set of vectors of 2 cross 2 matrices, and these set of vectors are linearly dependent. If they are linearly dependent, then find x. Very typical question, find x. But yeah. Okay, so if you have seen my previous lecture, what I taught, that these three vectors are dependent if a1 v1 plus a2 v2 plus a3 v3 is 0, such that at least one of them should be non-zero. At least one of the coefficient a1 a2 a3 is non-zero. Right, this is what I explained in the last lecture. Go watch that lecture. So this is the property of linearly dependence, that three vectors are linearly dependent, then their linear combination will give you zero vector with at least one of the coefficient a1 a2 a3 being non-zero. So we will apply the same concept in this question. All right, so if these are linearly dependent, then their linear combination alpha times the first vector, first matrix, plus beta times the second matrix, plus gamma times the third matrix. This is going to be 0 for any one alpha, beta, or gamma not equal to 0. At least one of them should not be equal to 0. Then the set the set is linearly dependent, right? This is the property of linearly dependence, that this set is going to be linearly dependent the if and only if the linear combination of these matrices is going to be 0 given that at least one of alpha, beta, gamma should be non-zero. If all of them are 0, then this is linearly independent, but it is given that this is linearly dependent. Okay. Now it's simple, right? We will simply solve this equation. We will solve this equation. So for example, alpha time x, we will get four equations for here. Okay. This is the first equation, alpha time x plus beta times 0 becomes 0 plus gamma times 1. This is 0 because the right hand side is 0, so it's all 0. I am simply multiplying these. If you are getting confused, so let me. I am simply going to multiply this thing inside. Okay, alpha time x minus alpha time x minus alpha 0 plus 0 minus beta x plus gamma minus gamma and 0 equal to 0. Right, now I will simply add this and I will get what I will get, alpha x plus 0 is 0 plus gamma, then minus alpha x minus beta minus gamma, minus alpha plus beta x plus gamma, and beta x 0 beta x 0, simply beta x, and this is 0. See, this 0 basically means it's a 0 0 0 matrix, right? So can also write this as 0 0 0 0. Okay, now this we will get four equations from here, right? The first one is alpha x plus gamma equal to 0. This is this one, right? Then I will get minus alpha x minus beta minus gamma equal to 0. The third one is minus alpha plus beta x plus gamma equal to 0. And the fourth one is beta x equal to 0. Okay, now let's check these four equations. Okay, first of all, in this scenario, we can say that x cannot be 0, right? For this equation, there could be two possibilities, right? Either beta is 0 or either x is 0, right? Either x will be 0, then this becomes 0, or either beta will be 0. But is it possible to for x to be 0? No. Why? Let us suppose x becomes 0. If x becomes 0, then what will be the first equation? This becomes 0 plus gamma equal to 0. So gamma becomes 0. Similarly, in the second equation, because x is 0, this is 0, gamma is already 0, so minus beta is 0, so that is beta also 0. And similarly, beta becomes 0, gamma becomes 0, so from third equation, alpha also becomes 0. So we have seen if x equal to 0, if x equal to 0, then alpha, beta, gamma all are 0. But it can't be possible it can't be possible for all alpha beta gamma 0, because it can't be possible because it's given to be linearly dependent. Because it's given these are linearly dependent, then at least one of the alpha beta gamma needs to be non-zero, otherwise it will be linearly independent. So hence we cannot say that alpha is 0, because if alpha is 0, from the above three equations, alpha beta gamma all become 0. If x is 0, then from the remaining three equations all alpha beta gamma become 0, and which cannot be possible because it's given linearly dependent. Okay, so if that is the case, then beta is 0. Okay, so if beta is 0, then let's check the equation 3. So this is equation 1, equation 2, equation 3, and equation 4. All right. So if now we have proven that beta is going to be 0, x cannot be 0. So if beta is 0, from equation 3, we can say that alpha minus alpha plus gamma becomes 0. So that means alpha equal to gamma, right? That makes alpha equal to gamma from equation 3. Now, if we place alpha plus alpha equal to gamma in equation 1, then what this becomes? This becomes alpha x plus alpha, because gamma is equal to alpha, so equal to 0, and this becomes alpha x plus 1 equal to 0, right? Now, what could be possible? Again, here there are two scenarios, right? Again, there are two scenarios in this case. Either either x plus 1 equal to 0, that that means x equal to minus 1, right? Either x plus 1 equal to 0, this makes x equal to minus 1, or alpha can be 0. But either alpha can be 0, right? But alpha cannot be 0. Why? Because if alpha becomes 0, now go to the first equation. If alpha becomes 0, this becomes gamma equal to 0. So alpha and gamma both become 0. And if alpha and gamma both become 0, then from equation to alpha, this term becomes 0. This term becomes 0, then beta also becomes 0. So, but alpha cannot be 0, because in that case, all alpha, beta, gamma are equal to 0, which is not possible, right? So we can say that only x plus 1 equal to 0 is the possible scenario, and hence x equal to minus 1. So we get the solution that x is minus 1. All right, so see how very interesting question this is. So we got x equal to minus 1. This is our solution. So this was asked in the question, right? What is x? So x is minus 1. So this is very important question, by the way. Just have this question in your notes. All right, very important question. Just pause the video and revisit it if you want. Okay, the fourth and the last question. It is saying that suppose we are given a linear transformation from R3 to R2. Suppose L R3 to R2 is a linear transformation with this thing. So the vector input vector 1 minus 1 0 mapped to 2 comma 1. Similarly, the input vector 0 1 minus 1 mapped by L to minus 1 comma 3, and so on and so forth. So see, you can see how this is from R3 to R2, because see, input vector is three-dimensional, 1 minus 1 0 0 1 1 1 minus 1, but the output vector is two-dimensional, 2 minus 1 minus 1 3. So this is a non-square matrix, by the way. The matrix representation of L is a non-square matrix, right? And it will be 2 cross 3, right? It will be a 2 by 3 matrix, because input is three-dimensional and output is two-dimensional. So if it is a 2 by 3, you can think L as a transformation which is taking vectors from R3, that is the three-dimensional space, and knocking them down into R2, that is two-dimensional space. So you can think that if you have this R3 space and you have a vector V here sitting in R3, and this transformation L is knocking them down into R2. So after this transformation L, it just get knocked down to this R2 plane. All right, so this is x, y, z, and this becomes x, y, and this becomes L times V. You apply the L transformation to V, and this becomes belongs to R2. So you can think that this transformation L is doing nothing, but it is knocking down the vectors sitting in R3 to R2. How beautiful it is. Very beautiful, right? You're just transforming a vector from one dimension to another dimension. It's like teleporting the vectors from one dimension to another dimension. That's how important linear algebra is for physics as well, because you will see vectors or things or objects moving from one dimension to another dimension. So in this case, you can see that L is moving V from R3, that is three-dimensional vector space, to a two-dimensional vector space. Very beautiful. Okay, back to the question. So it is given that this transformation L is moving these three-dimensional vector to these two-dimensional vectors from R3 to R2. Then the question being asked, what will be the transformation of this vector. Okay, so now this is also very important question. These types of tricky questions, these are very tricky questions. These types of tricky and concept oriented questions are always asked in GATE. So how we will proceed this question? Uh, we know this thing, right? We have seen this thing that in our previous question as well, in our previous lecture as well, that if we have a linear transformation, then alpha times v plus beta times w is nothing but alpha times L times of v plus beta times L times of w, right? This is a property of linear transformation. This is the property of linearity. We will apply the same concept here. Okay, so we need to find the linear transformation of this vector. So first of all, we will first of all we will write this vector as a linear combination of these three vectors. Why we are doing this? Because see, this the input vector space is R3 and these three vectors are linearly independent. You may be saying how, I mean, you can simply see this. Obviously, this is linearly independent with these two vectors, and these two are also linearly independent because there is no way you can scale this vector to get this vector. I mean, we will see a better way to find this linearly dependence and independence using rank in our upcoming lecture, but for now be with me. These three vectors are linearly independent, so they are spanning R3. So if they are spanning R3, we have seen in our previous lecture, if they are spanning R3, then any vector in R3 can be written as a linear combination of these three vectors, right? And we are doing the same here. This is one vector. I am trying to write this as a linear combination of these three vectors. So I will write it as alpha times the first vector, 1 minus 1 0, plus beta times the second vector, 0 1 minus 1, plus gamma times the third vector, that is 0 1 0. If I expand this, I will get it as alpha comma minus alpha plus beta plus gamma comma minus beta, right? And this is minus 1 1 2. Now you can simply solve this left hand side and right hand side. You will get alpha as minus 1, you will get beta as minus 2, and gamma as 2. You got the alpha beta gamma, so you got the linear combination of these three vectors to produce this vector. Very simple. Now the linearity property says that uh, if this vector is written as a linear combination of these three vectors, then the transformation, that is of L of these L then the transformation uh, the transformation of this vector can also be written as a linear combination of the transformed these vectors. Okay, that is alpha times L of the first vector, 1 minus 1 0, beta times L of the second vector, 0 1 minus 1, plus gamma times the transformation of the third vector, 0 1. This is the property of linear transformation, guys, by the way. Like, you take the linear transformation of the vector, it is same as if you have taken the linear transformation of the basis. You can think of these as basis vector. Okay, you can think this as basis vector, right? Because these are linearly independent and they span the entire R3. So you can the linear transformation of a vector is same as if you have linearly transformed the basis vector and taken the same linear combination. Okay, because here also we have taken the linear combination alpha beta gamma, right? Now all you need to do is just simply replace alpha with minus 1, and we already know what is L times 1 minus 1 0. L times 1 minus 1 0 is 2 1. Similarly, the remaining 2, this is already given in the question. So this is 2 comma 1, beta is minus 2, and this is 1 comma minus 1 comma 3. This is given in the question itself. Gamma is 2 and this is 0 comma 1. And if you simply solve this, you will get minus 2 plus 2 0, right, and minus 1 minus 6 2. So this becomes 0 comma minus 5. So hence done. So the linear transformation of this vector is nothing but this 0 comma minus 5. So I think these questions are clear to you. So which particular concept is applied in this question is the concept of linearity and linear transformation. For the third question, the concept of linear dependence is applied, right? For the second question, the concept of linear transformation. The second question is pretty basic, and the first one, the concept of linearity is applied. So I think we have covered very important questions. We covered four questions. Out of them, two are very important. The last two questions are pretty important because they are very concept-oriented questions, and such type of questions are asked in GATE. All right. So I think that's it for today. I think that's it for today. We have covered all the four questions. Okay. So if you like my videos, then please subscribe my channel, share with your friends, share with any GATE aspirant, whether it is for DA paper or any the other paper in which LA syllabus is there. Share with any ML engineer or AI engineer, it's helpful. Please share my channel, subscribe my channel, like my videos. It motivates me. It motivates me to create such more content. Okay. So see you next time. Bye.